Hello everyone, today we'll talk about the solution to the problem flip equivalent binary trees. Which is like, we don't want to flip binary trees that are equivalent, we are interested in binary trees that are flip equivalent. The flip, in this case, is just an exchange of left and right child in any node. So we can exchange subtrees that are children of any node, and we want to know that after some flip operations it's possible to get the two trees to look the same, or it's impossible. And it's important to note that the values of nodes are unique. If you don't see why this is important at this point, you might notice it later when you think about this problem. And in this problem there are at least two very general approaches, very general patterns that can be used to arrive simply at a solution. Maybe I'll start with the less general and maybe less intuitive one. But this flip of two subtrees is a little bit similar to swapping numbers in an array, and a question that would be similar to this question but in an array might be generally if two arrays, if one is a permutation of the other, if it's possible to transform one into the other. And we can solve that problem either by just counting the number of occurrences of every element. But another very useful solution, very useful idea, is that to check if two arrays are permutations of one another, we can just sort them both. And they are permutations, the original ones, exactly when after sorting they are the same. And this is called the canonical form. And we can do something very similar in this case. We can create a canonical form because node values are unique. And our canonical node might be that, well, we want the left subtree to be smaller than the right subtree. The root of the left subtree to be smaller than the root of the right subtree, always. And maybe if there is only one child, we want it to be the left child. Because in that case we can transform both our trees to that canonical form, and then we can just check if they are exactly identical. And also, of course, maybe it's possible to generalize the idea of counting number of elements. In this case, something equivalent to counting the number of elements is of course counting the number of occurrences of values, but also counting what values are, for instance, the parents of every node. So you might want to later think about if it's possible to do it like this, to see what are the parent-child relations, what nodes exist, and if it's possible to, by just calculating those values, answer the question. But an even more general approach, and an even simpler and more natural approach, that's in this case specific not to sorting and canonical representations, but specific to trees, is that we can have a simple recursive solution often. And in this case, indeed, we can have a recursive solution. Because at every node, and let's say that we have maybe had some parents and everything looks fine right now in two trees, then those nodes have two subtrees. And for the whole subtree rooted at one and the other node, we have to have that those two subtrees, maybe after swapping them, so doing the flip operation, are identical. So that this and this subtree and this subtree, as well as this and this, they are with each other flip equivalent. One subtree here is flip equivalent with one subtree here, the other here is flip equivalent with the other here, and of course the values of the root have to be equal. And in that case we know that those subtrees are also flip equivalent, those big subtrees. So that leads us to a simple solution. We can just check if left is compatible with left, right is compatible with right, and of course check the values. Or check if left is compatible with right and the right is compatible with left. One of those is necessary for the two bigger subtrees to be flip equivalent. The implementation is simple. Of course, if we have no more trees remaining, the answer is true. If there is only one tree remaining, the answer is false. If the values don't match, the answer is false. So those are the very basic ideas where where at least one tree that we have is empty, because then it's easy to decide. And of course we check the values. And now either, so this is the or, we have both flip equivalents between left and between right and right, or likewise between right left, and left right. And the final question, especially for the beginners among you, is what is the complexity of this solution? Because we can see something scary going on here, and that potentially scary thing is that we have recursive calls, and we have in fact as many as 4 recursive calls for every call of this flip equivalent. We eat one node from every tree, and we get 4 recursive calls. So what is going on here? And the answer is that node values are unique. And that means that there is at most one configuration of those 2 configurations that can be correct even at the first step. Or in other words, at least one of those 2 configurations will be excluded in those first checks, because either there is no more tree or the values will not be equal. And this is why in this problem those unique node values are important. And of course, because I didn't mention it in the previous option, in the canonical representation version, it's also this unique node values is important for the canonical representation, because in the canonical representation we want to be able to tell always which child should be the left one, and we cannot tell it if both the children have the same value. But values are unique, so we don't have to worry about it. One of the 2 existing children will have a smaller value. So this is the recursive solution, a very basic pattern, and not maybe that interesting, but still an important note about time complexity and about seeing one step further than just the fact that there are at most 4 calls for every recursive call, and in that case for every node of every tree.